Hi y'all, it's Ms. Blasky. Today we're going to be talking about the first part of topic 3.6. I think I'm going to split this over 2 videos. This one is going to be about the basics of gases and how we're going to handle gases and what's going on. So remember that gases behave, as we can assume, that they behave like there are no intermolecular forces between those particles. They're moving fast enough and they have enough space between them in order to not have any sort of intermolecular forces acting upon them. So 4 things that we can measure about a gas, and these are pretty specific to gases. Quantity of gas in moles, the temperature of the gas. Temperature is always going to be in Kelvin when we're talking about temperature, the volume of the gas in liters, and the pressure of the gas in atmospheres. Gas pressure is not always given to us in atmospheres. And so we have different conversions that we need to know to be able to convert back and forth. The biggest ones are millimeters mercury and torr, which are basically the exact same measurement, and kilopascals. The conversions that you need for these pressures are on your equation sheet, which we're going to be using a lot more now that we're doing math. Something that we need to be able to explain is what pressure actually is. And pressure is a force that happens when the gas particles hit the container. So gas pressure only happens when those particles hit the container. We do not create pressure when the particles bump into each other. So we have mathematical relationships for these 4 different quantities that we can measure about a gas: the moles, the temperature, the volume, and the pressure. You do not need to know the old dead white guys that are associated with each of these relationships, but you do need to know the relationships. So Boyle's law states that pressure and volume are inversely proportional, meaning that when pressure goes up, volume goes down. Got a little image here to explain that. Sort of makes sense that as we exert more pressure on a gas, we're going to be able to shrink the size of its container down because we're pushing on that gas. We're going to lessen the amount of space that that gas takes up. Now, notice that this relationship is only true if we have a constant number of moles and a constant temperature. So all of these 2 variable relationships are assuming that the other 2 relationships are held constant. Charles' law talks about volume and temperature. So when our temperature goes up, our volume also can go up. These are directly proportional, assuming that our moles and our pressure are staying constant. Gay-Lussac's law says that pressure and temperature are directly proportional. So if we increase the temperature of our gas, those particles are going to move faster. They're going to bump into that container more often, creating a larger pressure. Again, that's assuming that our moles and our volume are constant. And then the last one is Avogadro's law. Yes, that Avogadro. He said that the volume and number of moles are directly proportional, which means when the moles of a gas are increased, the volume that that gas takes up at constant pressure and temperature will also go up. More importantly, when we use Avogadro's law, usually what we're saying is that when we have multiple gases at constant temperature and constant pressure, if the volumes are the same, the moles are the same, or vice versa. If we have the same number of moles of gas at a constant temperature and pressure, then they will take up the same amount of volume. So we've got a little picture here showing that that is true. If I have argon, O2, and N2 gases all at the same volume, they're going to have the same number of moles as long as my pressure and temperature are constant. But notice that the mass of those moles is not the mass of those gases is not necessarily the same, because the molar mass of those gases is not the same. And if we put all of those relationships together about pressure, volume, temperature, and moles, we get the ideal gas law, or as I affectionately refer to it as Puvnert. We call these gases ideal meaning something that is perfect or the way that we want it, because we assume, again, we're making assumptions, that there's so much empty space between those atoms that the atoms themselves take up basically no volume. Now that's not actually true, but we can make a close enough assumption. And we make the assumption that they're moving so quickly that they are not attracted to each other or attracted to their container, that there's no intermolecular forces going on there. Again, not a perfect assumption, but pretty good for most situations and most gases. The times it does not work, and this is something that we need to know, when things deviate from the ideal gas law, are when we are at extremely low temperatures, meaning that those particles are not moving fast enough to be able to avoid having any intermolecular forces, or if we are at extremely high pressure, meaning those particles are crammed in close enough together that we're either getting really close to condensing that gas into a liquid, or the space in between those gas particles is now small enough that the volume of each individual particle is going to affect what's going on. Now, we don't have to do any sort of calculations when we have non-ideal gases, but we do need to know what situations those deviations from the ideal gas law occur at. We also need to talk about standard temperature and pressure, or STP. This is often used to help us simplify our calculations. Anytime we talk about STP, we are talking about 1 atmosphere of pressure and 0 degrees Celsius or 273 Kelvin. Now that is not room temperature. That is the freezing point of water, but we consider that to be standard. That's what we measure most of our gases at. So PV equals nRT, or PUVnert, works as long as we know some of the measurements about our gases, but we're trying to find one variable. We also can use the combined gas law, which this is not on your equation sheet, I don't believe, when we are talking about how these properties of the gases are changing from one situation to another situation. So we can derive this from using the ideal gas law and setting one situation equal to another. So P1 V1 over T1 equals P2 V2 over T2. So this would be, for example, if we had a gas at a certain temperature and a certain pressure, and then we changed the pressure, how would that affect the volume? So those are some of the basic calculations that you can go through with gases. We will be doing a lot of this practice in class. Gas laws are a big chunk of the AP exam, but I'm going to stop here for right now, and we'll come back later in another video and talk about Dalton's law of partial pressures. That'll be another video. See you later.